Hi guys. Okay, so this video we will cover chapter 5 thermochemistry, and that is the open Stax book, chemistry second edition, and we are looking at the learning check problems related to enthalpy 5.8 and till 5.12. Okay, when we talk about enthalpy, there are certain postulates, and you need to understand what enthalpy is represented as delta H. Delta H. And delta H has some values. If the value of delta H is negative, if the value of delta H is negative, that means that is the heat that is associated with a reaction that is exothermic. Exothermic reactions release heat. So how much of the heat is released? That is shown by the heat of formation of the product. This is the heat of the reaction, in which the heat of formation of the products minus the heat of the formation of the reactants. So in this case, the products have a lower heat of formation and the reactants have a higher heat of formation. So a small number when minus the big number, your answer is going to be in negative value. Okay, so that's the deal with delta H associated with the exothermic reaction. Sorry, this is not the exothermic. Okay, thinking fast. Okay, anyways, so here you have, if the value of delta H is a positive number, that means we are talking at the heat. We're talking of the heat that is associated with the endothermic reactions. So in this case, the sign of the delta H is a positive number. It's positive. So positive means that the delta H of a reaction is positive. That means when you do HP minus HR, that is the heat of the formation of the products minus the heat of the formation of the reactants, the products have a very high heat and the reactants have a low heat. This is the reason why you have to give a lot of heat to the reactants so that they can, break their bonds and form a new bond. So the products will be in a higher energy profile. Okay, so that's one thing. The second thing is that this also depends on the amount, the delta H value of a reaction also is depending upon the moles of the reactants and the products. So it's also associated with the number of moles of the reactants and the products. So in this case, for example, you have a reaction H2, which is in the form of a gas, reacting with half of O2. Now, half of O2 means only one oxygen atom. And this gives you H2O, which is in a liquid state. And the amount of heat that is associated with this delta H value is negative 286 kilojoules. So the units used here are kilojoules, very important. Second thing is the negative sign indicates that this is an exothermic reaction. So another way you can write this reaction is H2 as a gas reacting with half of O2. Half of O2 means only one of oxygen is used in making the bonds with, in this case, the bonds with H2O. Okay, and H2O is in a liquid state, plus another way of writing it is this, 286 kilojoules of heat. Okay, so in any case, in this case, the heat is a part of the product. Okay, so that's the, now the moles. Now, when we look at the moles here, the moles of the hydrogen, so there's only 1 mole of hydrogen reacting with half a moles of oxygen to give you the moles of 1 mole of water. So these moles are very important. How many are done? Okay. Next is that anytime we are reducing, anytime we are multiplying, if you're multiplying the moles, then you also multiply the heat of the reactions as well, or the heat associated with that. So the same coefficients apply to that. So next thing is that the physical state is also very important. Physical state of the reaction. So the heat that is associated with a substance in the gaseous form, in the solid form, in the liquid form, and in the aqueous form. Very specific and very different heats. So the physical state, so the amount of heat also, the physical state also determine the amount of heat that is associated with it. So we see that when 1 mole of hydrogen, so we can write this down as 1 mole of hydrogen, when it's in the gaseous state only, then it is going to react with half moles of oxygen, that also in gaseous state, to give you the water molecules. So in this case, the water molecules are, one second, if we say H2O, 1 mole of water in liquid state. If we say that, then, you know, the liquid state, then the amount of heat that is associated with it is very specific heat, and that is negative 242. Sorry, if it is in the gaseous state, in the liquid state is 242, but that's now changed. In a gaseous state means the vaporized state, vapors, water vapors. So in this case, it is negative 242 kilojoules. Now that is different from what you have seen on top. The top one was 286. So when water is in a liquid state, the heat associated with is the heat associated in a liquid state is 286, but in a gaseous state, it is 242. So you will write this down as G. This is G. This is G. Okay. So these are the basic postulates. Now let's look at these reactions that we start the learning check problems. So in this case, the question is that you are given a reaction. Zinc is reacting with HCl to give zinc chloride and hydrogen as a gas. And we need to balance this. So here comes this 2. And so this is a balanced reaction. Now here they are giving you 1.34 grams of zinc, 60.0 milliliters of hydrochloric acid, which is 0.750 molar. And this is giving zinc chloride 3.14 kilojoules of heat. Okay, so the question is, for 1 mole, how much kilojoules of heat is produced? So what are you going to do here? They have given you the grams, 1.34, and the heat associated with 1.34 grams of zinc chloride is 3.14. Now, anytime you're given these type of reactions, there's going to be some excess information. So in this case, we are only focusing on 2 things, which is the zinc and the amount of heat. So we are given the grams, so convert that. So the strategy is find the moles. First of all, the moles of zinc, then look at the mole to mole ratio of zinc and heat, and then find for 1 mole. The question is asking you that find for 1 mole, for 1 mole of zinc, how much of the heat is produced. Okay, so here we are going to first look at the, one second. We are going to take our the moles of the zinc. So let's do this in the blue color. So we have 1.34 grams of zinc times 1 mole of zinc over the molar mass of zinc. The molar mass of zinc is 65.3 grams of zinc. Okay, so that gives you 0.020 moles, and these are the moles of zinc. Okay, now for 1 mole of zinc, so this, so remember that how do I write this? 0.020 moles of zinc are producing 3.14 kilojoules of heat. Okay, so for 1 mole of zinc times, now this is going to become the conversion factor. You can create the 2 conversion factors from here. One would be 0.020 moles of zinc over 3.14 kilojoules, 3.14 kilojoules of heat, right? or 3.14 kilojoules of heat over 0.020 moles of zinc. So which one are we going to need? You're going to use, since we need to find the heat, so we are going to use this conversion factor. So just write this down now, that 3.14 kilojoules of heat over 0.020 moles of zinc. And when you multiply this 1 mole times 3.14 kilojoules of heat divided by 0.020, you get 157 kilojoules of heat. 157 kilojoules of heat. Now, pay attention to what the question is asking you, or what the question is saying. Sorry, what was that? When zinc reacts with HCl, the heat is produced. So that means this is an exothermic reaction. Sorry, heat is produced means this is exothermic reaction. So don't forget the sign. For the exothermic reaction where the heat is released, the sign of delta H is a negative number. So what is the answer? The answer is delta H is of this reaction is equal to negative 157 kilojoules of heat. That's the answer. That's the amount of heat that is released. So very important that you write the units. Very important you show the sign, okay? Because it's an exothermic reaction, so it's negative. All right, let's look at the next one. The next is, one second. Okay. All right, so the next is the question 5.9. And in the 5.9, you are given what is the enthalpy change. And this is problem 5.9 on page 257. So what is the enthalpy change when 1 mole of FeCl2 is produced? So in this case, first write the balanced equation, which is not given to you. So you write a balanced equation first, and then write down what is given. So we are given fluorine plus chlorine in both in iron in its solid state, reacting with chlorine in the gaseous state, giving you FeCl2 in a solid state, and the heat is released. So this is, as you can clearly see, the exothermic reaction. So in an exothermic reaction, the heat is a part of a product, okay? Or the value of delta H is, in both ways you can write. Either you can write it as 8.60 kilojoules as a product in a chemical reaction, or you can separate it outside. And if you're doing it, then the delta H is equal to negative 8.60 kilojoules. Okay, let's make this clear. 8.60, negative 8.60 kilojoules. So either way you can write the two. Okay. Next that is given to us is when 1.40 grams of iron, so write that down, reacts with 1.80 grams of chlorine, okay, 3.22 grams of FeCl2 as a solid is produced, and 8.60 kilojoules of heat is produced. What is the enthalpy change for the reaction when 1 mole of FeCl2 is produced? Now here, 1 mole of FeCl2 is produced, 1 mole, then how much of the heat is produced? Right now, the question is giving you, now here's a very interesting part. Ideally, this question is relevant to the, relates to the limiting reactant, okay? The amount of FeCl2 that is going to be produced is depending upon which is the limiting reactant, iron or the chlorine. So let's do it on the side first of all. Let's find the limiting reactant, and ideally that's how to do it. So let's do this here. So we have iron versus FeCl2, and we are going to do for the other one is the chlorine and FeCl2. Okay, so let's do, we are given 1.42 grams of iron, and convert first of all that to moles. So 1 mole of iron over 56 grams of iron, which you get from the periodic table, times the mole to mole ratio of iron and FeCl2 is 1:1. So 1 mole of FeCl2 over 1 mole of Fe. 1 mole of Fe times, now let's convert this to grams. So 1 mole of FeCl2 over the molar mass. So by this time, you should already know how to calculate the molar mass. So 126 grams is the molar mass of FeCl2. And this gives you 3.15 grams of FeCl2. Okay. Next is, you are given, next is chlorine. Let's do this here. Chlorine versus FeCl2. How much can you get that from here when you use chlorine, which is 1.80 grams of chlorine times, convert that to mole, 1 mole of Cl2 over 70 grams of Cl2 times 1 mole of Fe, 1 mole of FeCl2 over 1 mole of Cl2, because that's 1:1 ratio from the balanced equation. And here you have 1 mole of FeCl2, and here you have 126 grams of FeCl2. Okay, so this gives you 3.24 grams of FeCl2. So technically, you are, let's just do this calculations, grams and grams of Fe cancel out, moles of Fe cancel out, moles of FeCl2 cancel out. Here, chlorine cancel out, grams and grams cancel out, moles of Cl2 cancel out, moles of FeCl2 and moles of FeCl2 cancel out. And you are just left with the grams of FeCl2. Now you see that you should only obtain 3.15, but your book question is giving you 3.22, so you should ideally you be using 3.15 as a value. But anyways, it looks like maybe I don't know, maybe they took an average or something. But anyways, regardless, whether you use 3.15 grams of FeCl2, okay, when you do this FeCl2 3.15, or when you take 3.24 grams of FeCl2, you are still getting the same number of moles, which is, it's a very minor difference. So 0.0, the moles are coming out to be 0.025 moles. And that is of FeCl2. Okay, so you take these moles and do the molar ratio times the molar ratio. So so let's just do this, what is given to you. This is one way. So another way is actually, I need more space here. So give me 1 minute here. Okay, we want to make this really small so we know that we have done this on the side, checked for the limiting reactant. Anyways, so now we are looking at, let's just do now the setup the way we have it. So we are given, so just to use what is given to you, 3.22 grams of FeCl2 and convert that to moles of FeCl2. So 1 mole of FeCl2 is 1 mole of FeCl2 space, 1 mole of FeCl2 is 126 grams of FeCl2. Okay, and this is 0.025 moles of FeCl2. Okay, so 0.025 moles of FeCl2 is producing 8.60 kilojoules. So here we have this equality that 0.025 moles of FeCl2 is producing is equal to 8.60 kilojoules of heat. So this is your equality. And you're going to make the conversion factors from here. So you're going to write next thing is that 0. So for these moles, for 1 mole. So for the question is asking for 1 mole of FeCl2, how much of the heat is produced? So you're going to take the equality, 8.60 kilojoules of the heat is produced when 0.025 moles of FeCl2 react, okay, or FeCl2 are formed. So this gives you a total heat of 344 kilojoules. Okay, and remember that the heat is being produced. So in this case, the answer is going to be a negative number. But your book is giving you negative 338. I don't know how they got that. Maybe, you know, they were a little bit more, they didn't round up somewhere with the moles, but anyways, it's close enough. So negative 338 kilojoules is the book giving book. So I don't know how they're getting it. Okay, but anyways, your answer by this method is negative 344 kilojoules. So even if you do the limiting reactants, you still get the same answer. So just use, sorry. Oh, sorry about that. Okay, so just using what is given to us, we are able to get that. Okay, now let's look at the next problem, which relates to the enthalpy of combustion. Okay, now what is combustion? Combustion is a reactions in which the reactants, you know, generally it's the organic compounds, they react with oxygen, they are burnt and they give carbon dioxide and water, and a massive amount of heat is released. So in this case, enthalpy of combustion, how much heat is produced by the combustion of acetylene? So now acetylene, the formula for the acetylene is C2H2. Now, students who are in Chem 25 or students who are in Chem 1A programs, since we're not doing much of the organic chemistry, so we will give you the formulas for these. But even if they're not given, you can get them in the given tables. Even if we didn't give you the formula, we will give you the table. There's going to be some clues to it, so don't worry about that. But anyways, so now we are given the amount of 125 grams of this molecule C2H2. Okay, and we're being asked how much of the heat is being released. So in this question, you're going to refer to the tables, and these tables are containing the standard enthalpy values of combustion. Okay, so these standard enthalpy values of combustion, the molar enthalpies of combustion, that is for 1 mole. Okay, and that's for the exams, we will give you these values. So don't worry about that. You don't have to memorize, but as far as you know how to refer to them, where to look for this information. Okay, so what is known from this table? This is given. So look in the table, look in table on page 260. Yeah, page 260. So you are given or known as the C2H2 reacting with 2.5 of O2 to give you 2 moles of CO2, 1 mole of water, and 1301.1 kilojoules of heat is being released. Okay, so what do we do here now? In this case, another way, like I said, is writing the same equation is delta H is negative 1301.1 kilojoules per mole. Per mole is for 1 mole. Okay, so what is the strategy here? So first thing obviously is everything, you know, grams doesn't make sense. You always have to convert to moles. So take the grams of whatever amount, whatever substance is given, always convert it to moles using the molar mass. Next thing is look at a mole to mole ratio from the given reaction. Okay, so C2H2, 1 mole of C2H2 is giving you 1301.1 kilojoules of heat, right? Next is whatever moles you get in step 1, you apply them, and then based on that, you can get the heat. Okay, so we have the molar mass of C2H2. C2H2, 2 moles of carbon, times 12. This information, obviously, you get from the periodic table, and 2 moles of hydrogen times 12, and that gives you a total of 26 grams per mole. So here we see that, let's do this, convert, first of all, grams to moles of C2H2. So this is the first step. So we are given 125 grams of C2H2, okay, times, and this is times 1 mole of C2H2 over 26 grams of C2H2. And this gives you 4.80 moles of C2H2. Okay, so you see that in this reaction, 1 mole, this is 1 mole. 1 mole is giving you this much amount. So this and this are related. The rest of it, obviously, you need to balance the equation, always check that. Okay, the second step is that we know that 1 mole from the reaction, 1 mole of C2H2 is equal to negative 1301.1 kilojoules per mole. Okay, so that's for 1 mole, obviously. Okay, so for now, this thing is going to be your actually, just remove this. So your conversion factor from here becomes, the conversion factor is 1301.1 over, and it's negative is the sign of release, kilojoules over 1 mole. And that's C2H2. So that heat is very specific with the substance. Okay. All right. Next is, here we have the 4. So this is 4.80 moles of C2H2 times negative 1301.1 kilojoules over 1 mole of C2H2. So here we see that the moles of C2H2 cancel out, and we are just left with the unit of heat. So when you multiply this, you are going to get, the answer is 6254.80 kilojoules. Okay, so now you take this, convert this into scientific notation, and move the decimal 3 places. Move the decimal 3 places. Okay, so here when you move it, the answer becomes 6 point. So that's the value of delta H is equal to negative, the sign is still there, produced, yeah, negative 6.25 into 10 to the power 3 kilojoules. Now, why did I stop here? Significant figures. So if you look at it, this is the 3 significant figures. These are 1, 2, 3, 4, 5 significant figures. So your answer should have only 3 significant figures. Okay, so that's the answer. Okay. Okay, let me just make this here. This is the answer. And here is, this is the answer. Okay, now next is, so we got this done. Next is the standard enthalpy of formation. Now, what is a standard enthalpy of formation? So the enthalpy change for a reaction in which exactly 1 mole of pure substance is formed from free elements in their most stable states under standard state conditions. So standard state conditions are the STP, which is 1 atmospheric pressure. The temperature is 25 degrees Celsius. If you're looking at the molarity of the solutions, then it is 1 molar. Okay, so those are the volume is 22.4 liters, and if it's a gases. So those are the standard conditions. Now, These values are useful in predicting enthalpy change for dangerous or impractical chemical reactions. So sometimes it is not possible for us to do very difficult reactions because either we may not have the apparatus or the infrastructure for that, or the actual reactions are too dangerous to do. So extreme conditions. So what we do is we use mathematics to kind of make predictions based on what we know and what could be for those reactions, and generally they come out true. Okay, so here, for example, now what is the standard conditions? Besides that, there are also standard conditions in which the substances exist in nature, like they are nature made. So they are like, they are natural states. And natural states, like for example, oxygen is always going to be O2 as its more natural state. Hydrogen is always going to be O2 in its natural state. Okay, so chlorine, Cl2, is always going to be O2. So diatomic molecules is O2. So let me put this here. Diatomic molecules. So those diatomic, so that's their standard state. And then the metals, again, metals. In other words, we cannot make them. We cannot make them, so for the metals, in their most, for them, the standard enthalpy of formation of an element in its most stable state is 0. So iron, the most stable state of iron is 0. Aluminum, is solid, right? Aluminum is a solid. Copper is a solid. Silver is a solid. So in nature, they exist as solids. So in that case, we cannot manufacture. Of course, we can manufacture, but nature has made them in such a way that, so for them, the standard enthalpy change is 0. Okay, so just make a note of these. The natural state of these molecules are, solids and gases or liquids. Those, like mercury, its natural state is, so solid, liquid, gas, and then aqueous, obviously, when you dissolve certain things. But so those states, the delta H value is 0. And again, you have to refer in the tables. There are tables in the book, and it's in Appendix G, or we will provide you these values. So don't worry about it. Okay. So here, for example, graphite, the natural state of carbon is in the form of a graphite. That's carbon. And solid. Okay, so that's a natural state. Oxygen exists as a gas. That's a natural state. Carbon dioxide exists as a gas. That's a natural state. So when 1 mole of carbon reacts with 1 mole of carbon dioxide, it gives you 1 mole of oxygen, sorry, it gives you 1 mole of carbon dioxide, and it releases about 393.5 kilojoules of heat. So now let's look at these problems on page 263, and that is 5.11. So 5.11 is, you are given here the problem 5.11. The question is, hydrogen reacts explosively with gaseous chlorine, okay, to form hydrogen chloride. Okay, what is the enthalpy change for a reaction of 1 mole of hydrogen with 1 mole of chlorine if both the reactants and the products are at a standard conditions? The standard enthalpy of HCl as a gas is negative 92.3 kilojoules per mole. So what is given to you? You are given the standard heat of formation of HCl as a gas is negative 92.3 kilojoules per mole. Okay, so the question is, find the heat of a reaction. The question is, 1 second, what is the enthalpy change for the reaction of 1 mole? So if 1 mole of hydrogen and 1 mole of chlorine, if both of them react, and what is for this? So delta H for this reaction, in which you have hydrogen involved, chlorine is also involved, and you are producing the 2 moles of HCl. So 1 mole of hydrogen reacting with 1 mole of Cl2, and that's giving you 2 moles of HCl. Okay. Now remember that it's negative 92.3 kilojoules per mole. So for 1 mole is known, 1 mole of HCl, heat of formation for HCl in a gaseous form is equal to negative 92.3 kilojoules. Okay, that's the delta H value for the standard for 1 mole of HCl gas. So this is known or given to you. Okay, this will be given or known. Okay, so for 2 moles, what is the, so you just have to see, look at this. For hydrogen, the value of delta H, the heat, standard heat of formation is equal to 0. For chlorine, diatomic molecules, delta H, standard heat of formation is equal to 0. And then for 2 moles, how much is it basically in this reaction? That's what they're asking. So all you need to do is write down 2 moles from this reaction, 2 moles of HCl, okay, 2 moles of HCl times, you are given negative 92.3 kilojoules of heat when 1 mole of HCl is formed. So basically it's just a simple multiplication, and that gives you negative 184.6 kilojoules per mole. Okay. Next is, we are looking at the next question, 5.12, which is writing the standard heat of formation. So that is on page 200, 5.12 is, yeah, standard, writing the standard heat of formation. Okay, for the reaction. So here you are given this reaction. In this case, what is the formation of a reaction? Write the heat of formation. Write the heat of formation reaction equation for, this is given, C2H5OH, okay, in a liquid form. So that state is very important, okay? So remember that the delta H standard, the standard heat of formation is always for 1 mole, okay, is always for 1 mole when the reactants are in their standard conditions, like their most natural state, okay? The natural state, as we talked about. So for the graphite, the natural state is, the graphite, the natural state is solid carbon. Carbon exists in its natural state as a graphite, and which is solid. Phosphorus, the natural state of phosphorus is always solid, and it is P4. So these are the natural state. Oxygen, as we said, is always O2, and it's in the gaseous state. Iron is always solid in the gaseous state. So for these guys, the value of delta H is going to be 0. So anyway, so here we have this equation in which they are asking you write down the yeah, so formation of 1 mole. So remember, the question is asking you write for 1 mole. So you always have to choose, always this will be for 1 mole. The question is asking for the, write the heat of formation for this reaction, okay? So going back, how many carbons are there? There are 2 carbons, right? So write down, first of all, the initial constituents we have here. So we have the 3 main things here: carbon, hydrogen, and oxygen, right? So first write down, we have carbon, hydrogen, and oxygen. Write that down, okay? Next thing you are writing is the, there are 2 carbons balancing, and then there are 5 plus 1, 6 hydrogens. So you put this here, so that makes the 6 hydrogens, and then oxygens. Now we only need 1 oxygen, but we are given 2. So another way of balancing is half of oxygen, okay? So half of oxygen is just giving us half of O2. It means 1 oxygen. So once this is balanced, once this is balanced, you get this. This is the This is the heat of the formation equation. Okay, so that's basically what it is. Next is for N2CO3. Now N2CO3 is, again, let's do Na2CO3. So here you write down Na2CO3 is made up of sodium, is made up of carbon, and it's made up of oxygen. Now remember that natural state of oxygen is O2. Natural state of oxygen is O2, and it exists in a gaseous state. Carbon is in a solid state as a graphite, and sodium exists in a solid state in nature. Okay, solid in a graphite form, carbon and oxygen. And this whole thing gives you Na2CO3 as a solid. Okay, now balancing. So we would see we need 2 sodiums there, so you put 2 here. We have only 1 carbon, that's fine. Now oxygen, we need 3 oxygens here. So how do we balance this O2? So what you do is first, always, let's do this here. First, divide O2. So that gives you 2 that gives you 2 single oxygen atoms. That is half of O2. Half of O2 is 1 oxygen plus 1 more oxygen, right? So now you have broken this up. The second step is you are going to multiply by, now we need 3 oxygen. So now when we divide that division allows us to only look at 1 oxygen, but we need 3 oxygens. So in order to get 3 oxygen, you are going to multiply 1 oxygen, let's put this here, 1 oxygen, multiply 1 oxygen times 3. So that gives you 3 oxygens. So when you put, so this whole thing becomes multiply, half oxygen by, so how do I do this? So in other words, this is the way, 3 times half is equal to 3 by 2. So this here is 3 by 2. And this 3 by 2 is actually 3 oxygens. In other words, there's another way of looking at it. 6 oxygens, right? And then half of 6 oxygens is equal to 3 oxygens. So this is this. So this is, looking at the fractions from that perspective. All right, so we talked about the enthalpy a lot, and we see that, when we look at these problems, are fairly simple problems. It's just important thing is molar. So our next video is going to be on Hess law, and then, that's going to finish this chapter. All right, thank you for watching. Bye-bye.